When we're dealing with sets of objects that have particular objects that repeat in that set, we need to make a slight adjustment to account for the fact that we can't tell the difference between identical objects. So if we have the word two, there is two O's in that word. The O repeats. If I were to tell you that the second time I wrote it, I swapped the positions of the O's, you would probably tell me that I was crazy, and this is the same thing. And this is why we have to treat this situation slightly differently. So if we have a set of objects, A in total, and a subset of them, B, repeats, and another subset, C, repeats, then to figure out the number of ways you can arrange them that are unique, you take the total number of objects, do the factorial of that number, and then divide by the factorial of each repeating object. Let's have a look at this example. How many ways are there to get from A to B? So there's a number of ways that you can approach this question. You can do it right off the diagram, or you can use this formula that we just introduced. So working off the diagram, I'll show you that way. To get from A to here at this intersection, there's one way to do that. To get from A to here, there's one way to do that. To get from A to this point, there's one way to do that. So we're only allowed to move either south or east at each intersection. So there's only one way to get to all of these intersections across the top, and there's only one way to get to all of these intersections across the side. Now if we want to get to this intersection from A, we can either take this route or this route. So there is 1 plus 1, 2 ways to get there. If we're looking at the number of ways to get to this intersection from A, we can take this route, we can take this route, or we can take this route. Or 1 plus 2, 3 ways. And then we just continue on like this for the rest of the diagram. So 2 plus 1 gives 3 plus 4. 56 and 28 is 84. So there is 84 total ways to get from A to B on this grid. The other way we can do this is notice that we have to go 1, 2, 3, 4, 5, 6 times east, and 1, 2, 3 times south. So no matter which route we take, we're going to have to go 6 times to the east and 3 times south. Now 6 times east, we repeat going east 6 times, so we have to divide by 6 factorial. And we repeat going south 3 times, so we divide by 3 factorial. This will give us 9 factorial divided by 6 factorial and 3 factorial. So on your calculator, you've got 9 factorial divided by 6 factorial and 3 factorial. So that gives you 84 as well. Here's another example. How many ways can you arrange the letters in the word arrange? So arrange has 1, 2, 3, 4, 5, 6, 7 letters total. If we were somehow able to slap a label on each of these letters, and we were able to tell the difference between the A's and the R's, the number of ways to arrange that would be 7 factorial. But since the A repeats twice, and the R repeats twice as well, we need to divide by 2 factorial once for the R, and 2 factorial for the A. So on your calculator, you've got 7 factorial, divide by 2 factorial, which is just 2, and another 2 factorial. So 1260. There is 1,260 ways to arrange the letters in the word arrange. When you want to select a certain number of objects from a larger set and don't care about the order, you use combinations. So you use combinations when the order does not matter. Situations where you would use this include poker hands, committees, making a smoothie. So if you have 2 ingredients, strawberries and bananas, it doesn't matter in the end whether you have bananas added first and then strawberries, or if you put the strawberries in before the bananas. You just care if they are there or not. So that's really the essence of combinations. So the formula is basically the same as the permutation, but we divide out the number of permutations of the R objects that we choose at a time. So the function on our calculator, you hit math, go to the left one, and then choose 3. Let's say you have 4 ingredients: strawberries, bananas, oranges, and mangoes. If you want to make a smoothie consisting of 2 of those fruits, you have 4 objects in total, and you're choosing them 2 at a time, so you can make 6 possible smoothies from those 4 ingredients. You don't care about which order you put the ingredients in, you just care whether they are there or not. So here's an example. How many ways can 6 people be selected from a group of 14? So in this case, we have 14 total people to choose from, and we're taking them 6 at a time. We don't care which order we pick them in, as long as they're in the group, that's all we care about. So on our calculator, we have 14 people. We're choosing them 6 at a time. There's 3,003 ways that you can take 6 people from a group of 14. Here's another example. How many 5-card poker hands are possible from a standard deck of cards? So we have 52 cards in the standard deck, and we have 5 cards in a poker hand. So we choose these cards 5 at a time. It doesn't matter which order we get these cards in. So 52 choose 5 is the total number of poker hands that we can get. So there's 2,598,960 poker hands. Here's another example. We've got 12 girls and 8 boys in a class. How many committees of 5 contain at least 3 boys? There are a few scenarios that we need to address in order for the group to contain at least 3 boys. So one possibility is 3 boys and 2 girls. Another possibility is 4 boys and 1 girl. And then the last possibility is a group of 5 boys. So in order to figure out how many ways we can arrange for 3 boys and 2 girls, we've got 8 boys, choose them 3 at a time, and 12 girls, choosing them 2 at a time. So 3 plus 2 gives us a group of 5. We're choosing 3 boys from 8 and 2 girls from 12. The next situation we have to look at is a group of 4 boys and 1 girl. So we have 8 boys choosing 4 at a time, and 12 girls choosing 1 at a time. So 4 and 1 will give us a group of 5, and then we're choosing 4 boys from a group of 8 and 1 girl from a group of 12. So then the third situation we need to deal with is a group of all boys. So we have 8 boys, choosing them 5 at a time, for a total group of 5. So in order to calculate the first situation where you've got 3 boys and 2 girls, you 8 choose 3, and then multiply that by 12 choosing 2. So this gives us 3,696. The second situation, when you add that up, is 840. And then the third situation, you get 56 different ways to do that. So we can either have a group of 3 boys and 2 girls. That's the number of ways we can arrange that to happen. We can have a group of 4 boys and 1 girl. That's the number of ways to do that. Or we can have 5 boys. So either this situation or this situation or this situation will work. So we need to add this number and this number and this number. So when we add all of these numbers together, we get 4,592. This is the number of ways that you can pick 5 students with a group of at least 3 boys. We can use the ideas that we learned in this unit to calculate the likelihood of certain events happening. So we can use fundamental counting principle, we can use permutations, combinations, and permutations with repeats in order to figure out probabilities. In order to do that, we find the number of ways that a favorable outcome can occur and divide by the total number of ways that any possible outcome can occur. Let's have a look at an example. If we want to determine the probability of being dealt 8 hearts from a standard deck of cards, we want 8 hearts. That is the favorable outcome. So the number of ways that you can get 8 hearts from a deck of 52, well, there is 52 cards total in a deck, and there's 13 that are hearts. To find out the number of ways we can be dealt 8 hearts, we have 13 possible hearts to choose from, and we want them 8 at a time. So that's the number of ways that we can get 8 hearts from a standard deck of cards. Now the number of ways that we can get 8 cards of any suit, any combination, is 52 total cards choosing 8 at a time. So 13 choose 8 will give you 1,287. So that's the number of ways you can get a hand of 8 hearts. And then the total number of 8 card hands is 752,538,150. When we divide these two numbers, we get the probability as a decimal. So it's 1.7 times 10 to the negative 6, or 0.000017. Here's another example. What is the probability of getting a flush in poker? We can have a flush occur in either hearts, diamonds, spades, or clubs. So there is 13 choose 5 ways that we can get a flush in hearts. There is 13 choose 5 ways that we can get a flush in diamonds. There is 13 choose 5 ways that we can get a flush in spades. And there is 13 choose 5 ways that we can get a flush in clubs. So either this or this or this or this is a favorable outcome. So we can have a flush in hearts, diamonds, spades, or clubs. So if it's or we're concerned with, either this or this or this will work. So we add those numbers together and we divide by the total possible ways that we can get a 5-card hand. This will give us 5,148 divided by 2,598,960. So it works out to be, as a decimal, 0.00198. So it's about a 0.198% chance that you get a flush in poker. So last example, what is the probability of getting 2 jacks and 3 queens in a poker hand? So there are 4 jacks and 4 queens. If we want just 2 jacks, there's 4 of them total we can choose from, and we want them 2 at a time. And there is 4 queens as well total, but we want those 3 at a time. So we want 2 jacks and 3 queens. So we need to multiply these numbers together, and then we divide by the total number of possible hands that we can get in poker. So it's 5 cards at a time. This will give us 24 possibilities out of 2,598,960. So this works out to be 9.23 times 10 to the minus 6. So this is the probability as a decimal of getting this hand in poker.